In this video, we'll wrap up our discussion of Newton's method and generalize it to the case of vector value theta, and we'll apply it to logistic regression. Earlier we worked out this was a cost function for logistic regression, and we said that if theta is a real number, then this is one iteration of Newton's method. Let me just write down the generalization for the case of theta is a vector of parameters rather than just a real number. And to motivate this, if you look at this formula, right, this is theta minus essentially the first derivative minus the second derivative of j. So it turns out that the vector value generalization looks pretty similar, in which theta t plus 1 is equal to theta t minus h inverse and then this derivative vector, and where this, so the way to pass this is a matrix inverse and then times that's a vector, okay, where this thing is called the gradient vector, and this is just the vector of partial derivatives of theta with respect to theta 0, theta 1, and so on down to theta n. And so this is going to be an n plus 1 dimensional vector. So this is n plus 1 dimensional vector. And H is going to be an n plus 1 by n plus 1 matrix. So H is going to be a matrix, n plus 1 by n plus 1, where Hij, that is the I comma j elements of H, right? So H is a matrix. So it's H11, H12, and so on, and H21, and so on, right? This is a matrix. And somewhere in this matrix, you know, well, each element Hij of this matrix is defined as the second derivative of j with respect to theta i, theta j. So this is the matrix of second derivatives, and thus this formula captures this intuition of taking the first derivatives and then, you know, dividing by the second derivatives, really multiplying by the inverse of the second derivatives. And this matrix H is also called the Hessian. So H is called the Hessian matrix, or the Hessian of J. So given these definitions of H and of the gradient vector, if you know enough calculus, what you can do is look at this definition for J and take the first derivatives, and that'll give you this gradient vector. And you can also, you know, compute all the second partial derivatives. You know how to do that, and that'll give you this matrix H. And if you work out all those formulas, you can then implement this and get Newton's method for logistic regression. I've already done the work of taking these partial derivatives, and so, you know, feel free to check my math if you want, but let me just tell you what you get if you take those partial derivatives. What you get is that you can compute this vector as, and this notation means the derivative of j with respect to theta. This funny, you know, notation I've written, this is just a vector. So, but it turns out you can compute that vector of derivatives as this, and hopefully this will be little surprise to you. And so that's an n plus 1 dimensional vector. And the matrix of second derivatives, the Hessian matrix, I've already figured out how to compute it. It turns out that the Hessian matrix is given by this formula. I'm omitting theta here just to simplify the notation. You can write a subscript theta there if you want. Times xi transpose. Okay, and so this is a formula. Let me just say what each of these terms mean. I'm going to put square brackets there. Let me just say what each of these terms mean. So that is a real number. It's a prediction of your hypothesis on Hi. That is also a real number. This thing over here, right? This is going to be an n plus. That's going to be a n plus 1 by 1 vector, and this is going to be a vector transpose. So what you get, this is a tall vector. This is Hi. This is Xi. And Xi transpose is going to be, you know, a y vector like that. So this is Xi transpose is going to be R of 1 by n plus 1. And so if you multiply these things, if you multiply these two vectors together, you actually get out a big matrix, which is a n plus 1 plus 1. And when you sum up all of these things, real number times this matrix, what you end up with is the Hessian matrix H. And once again, if you want to check the calculus, it's a slightly tricky calculation, but if you're good at calculus, you'd be able to do this. Should I check that the ij element, right? So this matrix, this formula here defines the H matrix, and it turns out the ij element of this matrix is equal to that second partial derivative. Finally, having computed the vector in the matrix, you can then update your parameters theta as follows, times delta theta j, and that's one iteration of Newton's method. It turns out Newton's method converges very quickly. Let me just give, in the previous video we saw one intuitive view of Newton's method as solving for when the derivative is equal to 0. Let me give a different sort of cartoon picture illustration of another picture showing what Newton's method is doing. So we have a function j of theta, and we want to find the minimum. So we find that point. And let's say we start off, over here, right? Let's say we start off with a value of theta over here. So this is theta 0 over here. So it turns out one view of Newton's method is it looks at this point, it looks at the first and second derivatives of your function, and it then fits a quadratic function that matches your function's first and second derivatives at that point. Okay, so it'd be just kind of tangent to it, I guess. And then what it does is it minimizes this quadratic function, and so you end up minimizing it and moving over here, and that's theta 1. Now at this new point theta 1, you again look at this function and you fit a quadratic function that matches your function's first and second derivatives. So I'm not drawing that very well, but you get the idea. So this gives you a different quadratic function, and you then minimize this green quadratic function, leading you to a third point over here. And then you again look at this, and you fit something that matches it, fit a quadratic function that matches its first and second derivatives. You then minimize this purple quadratic function, and you end up over there. This is very close to the, which is maybe not exactly, but very close to the global minimum of j. Okay, so I didn't draw this very well, but I hope it makes sense. There's j, and on each iteration you're at some point, and what Newton's method does is it fits a quadratic function that matches your function's first and second derivatives, minimizes that, and that's one iteration of Newton's method. And this can tell, right, this algorithm converges extremely quickly, especially when your optimization function j is convex. And in practice, for many logistic regression problems, I don't know, when I run it, seeing it converge in, say, 5 iterations is fairly typical. When I run logistic regression with, I don't know, anywhere from 1 up to maybe 100 or maybe 1,000 features, seeing rapid conversions like this. And it depends on your data set and depends on a bunch of other things, but converging in a smallish number of iterations is fairly typical. So to wrap up this video, I have one question for you, which is, we'll talk about Newton's method and how it converges fairly quickly. So my question is, well, how do you check if Newton's methods really converge? Of the methods below, which do you think is the best one for checking if it has converged? Hopefully you got that this last choice is the right answer, and in particular, as we often do, for gradient descent as well, you can plot your optimization objective as a function of the number of iterations and check that it has flattened, and check that it has flattened out, right, where the horizontal axis is the number of iterations. And this is often a good way to test it has converged. And all of these other things, I just want to point out the second choice, plotting j of theta as a function of theta. Well, that's actually incredibly difficult to do if theta is a high dimensional vector, right? So if theta is a 100-dimensional vector, well, we can't really plot this. If theta were a real number, then maybe you can plot it, but if theta is a high-dimensional vector, that's hard to plot, and that's why this fourth answer is what I would use to check convergence. So you now know how to implement Newton's method, and with this also check how it converges. Using this method, you'll be able to very quickly find a good setting of the parameters theta for logistic regression.